Welcome to the Problems channel, Season 2, Episode 41. The episode which I titled 5 coprime odd numbers that live on a globe for the reason that will become apparent momentarily. But before we deep dive into the underlying mathematics of this episode, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence and welcome to our channel. And second of all, it is a good idea for you to go to the homepage of this channel and in the channel's trailer section find the episode titled The Problems Channel How To. Watch that episode in its entirety, follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do on this channel. In the mathematical problem S2E41, we're given a set of whole positive numbers designated as AI with the following three properties. All such numbers are odd, which means that all these numbers are missing the prime factor of 2 in their prime factorization. All such numbers are coprime with 5, which means that all these numbers are missing the prime 5 in their prime factorization. And all these numbers vary between 1 and 100. Consequently, each such number is multiplied by pi once, by one copy of pi. The result of this multiplication is divided by 100, or one copy of 100. And this new real number becomes the argument to the trigonometric function of cosine. And all such trigonometric functions of cosine are strung together into a finite product. And the challenge in the problem, in the mathematical problem S2E41, is to unmask the name of the real number that sits on the other side of the equal sign of this finite product. And again, in the big scope of things, in the mathematical community at large, no one really cares about the number that sits on the other side of the equal sign of this finite product. But in the mathematical community at large, everyone cares about your ability to generate a convincing story behind why the number that sits on the right hand side of the equal sign of this finite product is what it is, using the divide and conquer problem solving approach. In the previous episodes, we already explained that if we want to apply the divide and conquer problem solving approach to the process of generating of a solution of this or that technical problem, we should try to carry out the following three steps. First, we should try to divide a whole into a number of smaller and simpler primitive parts. Step number two, we should try to generate the solutions or all the solutions of all the smaller and simpler primitive parts. And as the third and the final step, we should try to find a way to combine the solutions, or find a way to combine all the solutions of all the smaller and simpler primitive parts into a solution of the whole. Consequently, if we want to apply the divide and conquer problem solving approach to the process of generating a solution to this problem, then the first order of business is to identify what the proverbial whole in this problem is. Evidently, as we noticed in the previous segment, sometimes we're given that proverbial whole explicitly. Sometimes we are not given the proverbial whole explicitly, but that whole literally lies on the surface. We move a couple things about, oh, there it is. And sometimes we have to apply an effort of varying degree in order to uncover a fruitful whole. In this case, however, the proverbial whole, that is one of the main characters of the divide and conquer problem solving approach, is pretty much given to us. We know that the whole in this case is the finite product shown over here, or a finite product of the values of the trigonometric function of cosine, each of which is evaluated at the argument that is constructed as we explained in the previous segment. That is our whole. And what are the smaller and simpler primitive parts in this whole? Well, it is tempting to say that the smaller and simpler primitive parts in this case are evidently or obviously the values or the individual values of the trigonometric function of cosine. Here, however, when we deal with products, whether these products are finite, which is the case in this problem, or infinite, we have to be quite careful because sometimes it can so happen that in the string of factors that make up a product, whether that product is finite or infinite, we can sometimes introduce, for example, a number in the numerator in one place and then the same number in the denominator in the other place. Somewhere here there is another number and somewhere else this similar number in the denominator. These numbers cancel each other out and thus they seemingly disappear from the view. But if we do introduce these numbers and then we shuffle things around, we may come across a tactical advantage in the process of solving this or that problem. But in this case, as a first cut, we will take it that the smaller and simpler primitive parts are precisely the values of the trigonometric function of cosine, each of which is evaluated at the argument shown over here. And the interesting question is how many such trigonometric functions of cosine are in this finite product. Now, it is possible to approach the solution of this problem from two different directions. From one direction, we can work specifically with the numbers that are given to us. And from another direction, it is possible to work as generically as possible and replace the given numbers with their proverbial abstract notation, such as n, for example, and then solve the problem in general, and then reduce the solution of a general problem to a solution of the specific problem that is given. And that is an approach that we will favor throughout this channel in many other problems. But in order to make this solution of this problem accessible to as wide an audience as possible, I will show a solution that is approached from the angle of the specific numbers that are given. But in general, I'll make a remark that we can notice that the numbers 2 and 5 are precisely the prime factors of the number 100. And that means what? That means that the numbers AI are precisely all the whole positive numbers in a given range that are coprime with 100, and which popular mathematical function returns that value. Exactly, the Euler's tangent function returns precisely the number of whole positive numbers coprime with n, and it is always possible to mechanically look up that number. The value of the Euler's tangent function evaluated at the argument 100 is 40, but initially it pays to step up close and develop an intimate relationship, if you will, with these mathematical objects early on. So let us do that together right now. It doesn't take much time, and it actually will benefit us in the long run when we understand how the solution, my solution of this problem unfolds, which again, I will try to reduce it to the middle school level and avoid dealing with complex numbers, because this problem can be solved using complex numbers. But again, not that many people know what the complex numbers are, and among the set of people who know what complex numbers are, if you decide to solve this problem using complex numbers, inevitably you will come across the so-called cyclotomic polynomials. And among people who know about complex numbers, how many people know and truly understand what a cyclotomic polynomial is? As such, as simple as possible, but not simpler, at the proverbial middle school arithmetic, we begin. Between the numbers n1 and 100, we have how many blocks of consecutive whole positive numbers that run in tens. Well, we have 10 such blocks. One such block runs from 1 to 10. Another such block will run from 11 to 20. The other such block will run what, from 21 to 30 and so on, all the way to the 10th block of consecutive whole positive numbers that run from 91 to 100. 10 blocks, 10 strings like this, and in each such block we have 10 numbers as well. 10 times 10 is 100. Within each block of 10 consecutive whole positive numbers, how many numbers do we have that have 5 in their prime factorization? Well, evidently precisely 2. For example, here we will have 5 and 10. Here we will have 15 and 20. In other words, 5 has the prime factor of 5 in its prime factorization. 10 has the prime factor of 5 in its prime factorization. 15 has the prime factor of 5 in its prime factorization. 20 and so on. Here in this block we will have what? 25 and 30 and so on, blah blah blah, all the way to 95 and 100. Evidently, by the multiplication counting principle again, we have 10 blocks, each of which has 2 numbers which have the prime factor of 5 in its prime factorization. Consequently, how many numbers between 1 and 100 will have 5 will have the prime factor of 5 in their prime factorization? Well, 10 times 2 will be 20. 20 numbers, in plain English, divisible by 5 between 1 and 100. Within each such pair of numbers, 2 numbers, 2 numbers, 2 numbers, and 2 numbers, how many such numbers will be odd and how many such numbers will be even? Well, within each single pair, precisely one, let's say, middle number will be odd, and the edge number will be evidently even, which means what? Which means that between the numbers 1 and 100, there will be precisely 20 over 2, 10 numbers that are odd and that have the prime factor of 5 in their prime factorization. That's on the one hand. On the other hand, between the numbers 1 and 100, how many odd whole positive numbers do we have? 50. Evidently we have 50, and that means what? That means that 50 numbers are odd between 1 and 100. But from that number of 50 odd whole positive numbers, we have to subtract what? We have to subtract 10, because this is the number of the whole positive numbers that have the prime factor of 5 in their prime factorization. And we're told that none of our numbers do have 5, the prime factor of 5, in their prime factorization. Therefore, 50 minus 10 comes out to precisely 40. 40 is the number of the smaller and simpler primitive parts in this whole, which is represented by the finite product of the values of the trigonometric function of cosine. Now that we identified our whole and we managed to count the number of smaller and simpler primitive parts, which in this case comes out to be 40, we can move on to our second step of the divide and conquer problem solving approach and try to figure out how we can solve each and every smaller and simpler primitive part. Now that in the previous segment we generated the number of smaller and simpler primitive parts that make up the whole, which is represented by the finite product of the values of the trigonometric function of cosine, each of which is evaluated at the argument shown over here, I would like to make a remark that ideally, of course in practice this virtually never works out that way, but ideally during every stage of fighting for generating a solution of this or that problem in mathematics, theoretical physics, and computer science, it pays to have a clear mental image of what exactly we're dealing with and what is going on in the underlying problem. In order to generate that clarity, it pays to write down the set of the numbers AI that are given in this problem explicitly, and I wrote down that set for you guys over here. That set is 1, 3, 7, 9, 11, 13, 17, and so on, 93, 97, 99, which is what? This set is the embodiment of the return value of the Euler's Tauchian function evaluated at the argument of 100, which is basically a set of all the whole positive numbers between 1 inclusive and 100 that are coprime with 100. Consequently, we take the set of the numbers AI, and each number in that set is multiplied by 5. The result of that product is divided by 100. So the set of arguments of the trigonometric function of cosine is listed over here. It's basically the same numbers, but with the 5 over 100 tacked onto these numbers. Pi over 100, 3 pi over 100, 7 pi over 100, 9 pi over 100, 11 pi over 100, 97 pi over 100, 99 pi over 100. Now, the notion of cardinality of a set was introduced in order to deal with the so-called infinite sets. In our case, we have two sets that are finite, and in this case, the cardinality and the size of the finite set, of the underlying finite set, is basically one and the same thing. It's the number of elements in each set. The number of elements in each set is one and the same. And as we computed in the previous segment, this number is 40. And now, in order to carry out the second step of the divide and conquer problem solving approach and find a way to solve each and every smaller and simpler primitive part, I asked the following question when I was solving this problem. What is the popular geometric interpretation of this here real numbers? A popular geometric interpretation of, let's say, one-dimensional, if you will, real numbers is the proverbial number line. Number line, which we, let's say, pick this way, designate it somehow. We designate the origin of this number, we just designate the scale 1, and so on. So in theory, our numbers are somehow sprinkled over that number line, but because both of our sets at hand are finite, that means that what is one popular geometric interpretation of our sets? One popular geometric interpretation of our set is actually a line segment. A line segment, which pi over 100, it's a number that is close to 0. Let's say somewhere over here it begins, and somewhere over here it ends. It doesn't really matter. This is our geometric interpretation of the numbers, each of which becomes the argument to the trigonometric function of cosine. And how do we gain a tactical advantage, and how do we think out of the box when we try to solve this problem? Well, here's my idea. And again, as I explained in season 1, episode 2, how to practice mathematics correctly, I suggest that you do not just listen to my solution continuously non-stop, but try to apply your personal effort. If you were not able to solve this problem correctly on your own using the divide and conquer problem solving approach, as simple as possible but not simpler at the middle school arithmetic level, then here is a hint. One tactical maneuver that represents a lightweight thinking out of the box in this case is actually quite popular in mathematics and in computer science, and we will see the problem in computer science which can be solved elegantly using that maneuver, is to take our line segment and do what? And bend it into a circle. Huh? What does that mean? Take a line segment and bend it into a circle. Well, that was actually the first hint for you guys, so I suggest that you put this video on pause, walk away from your computer, think on your own, see if you can carry the solution through on your own without my help. And if that hint is not enough, then the second hint that should make things clear where this is going, we take the line segment and bend it into a circle, and we use which popular trigonometric identity. For all real numbers theta, it is the case that pi minus theta is equal to minus cosine of theta. You see, this is our first, if you will, divide and conquer workhorse formula, and I will explain how does this formula bend the line segment into a circle and what follows. And the moment I explain it, you guys will understand why I titled that episode in this specific way. Here is my idea, and if you have a better and brighter idea, then do not be shy and feel free to share your beautiful idea with our community in the comment section. I suggest that we take the set of numbers between 1 and 100 that are coprime to 100. We put these numbers onto the number line segment, and then we bend that line segment into a circle shown over here in blue. And that circle becomes a model of one and the same meridian of a planet over which we distribute our 40 numbers coprime with 100 uniformly. Because remember that technically on the number line or on the number line segment, these numbers are not distributed uniformly, but here when we put these numbers onto one and the same meridian of a planet, we sprinkle them uniformly. And because that number is, the number of numbers is even 40, it is possible to divide our planet into two logical halves or into two logical hemispheres. The hemisphere that you see on your right, I will refer to as the green hemisphere, and the hemisphere of this planet that you see on your left, I will refer as the red hemisphere. In the green hemisphere, they live the first 20 numbers between 1 and 100 that are coprime to 100. And these numbers run 1, 3, 7, 9, 11, and so on, all the way to 43, 47, and 49. The last green number will be 49. And in the red hemisphere, they live the remaining 20 numbers between 1 and 100 that are coprime with 100, and these red numbers run 51, 53, 57, 59, 61, and so on, all the way to 91, 93, 97, 99. Again, because the number of numbers is even, we split them into two equal halves. We distributed these numbers over the meridian of our planet uniformly. We do that in such a way that any two numbers that live on the same parallel, shown over here in yellow, for example, this parallel and this parallel, this parallel, and this parallel, any two numbers that live on one and the same parallel sum to 100. This is our design, this is our choice. In other words, in every such pair, one red, one green number that live on the same parallel, these numbers sum to 100. Now, this is a purely logical visual device, and recall my previous comment that I made in the previous segment about having a mental clarity or having a clear mental picture of what are we working with. And this is precisely the purpose of this logical visual device, to produce the clarity of understanding of what we're working with. So what does this logical visual device buy us? Well, as a hint, remember I gave you guys this hint that for every theta real, we have the following identity. So now let us work that identity right to left this way, which means that the negative, the minus sign will come to this side. Starting, we'll apply this identity to all the numbers, to all the red numbers, 51, 53, and so on, all to 99. And of course, we understand that in general, pedantically or technically, these numbers over here have to be scaled by pi divided by 100. But in order to avoid the clutter, I wrote down just the numbers themselves, and we will understand what that means. As such, the cosine of the first red number over here, what will it be? It will be cosine of 51 times pi over 100, and according to this formula, which we read right to left, this will be what? Negative cosine of pi minus 51 times pi over 100. And what do we do now? We bring all the numbers in this relation to one and the same denominator, which is 100. 100 pi minus 51 pi over 100 comes down to what? Minus cosine 100 pi minus 51 pi comes down to exactly 49 pi. 49 pi over 100. In other words, what we just proved is that the cosine of this here red number is equal to the cosine of the number that sits on the same parallel multiplied by -1. What do we do next? Well, we carefully step through the red hemisphere and we apply this transformation to all the red numbers, and we will do that together just for the first few red numbers. Our next red number is 53, and that number lives on our planet on the same parallel as what number? As 47. And precisely because 53 and 47, 53, the red 53 and green 47 sum to 100. When we transform the cosine of 53 times pi over 100, we obtain what? Negative cosine of pi minus the same argument. We bring these two numbers to one and the same denominator, and what do we have? Negative cosine 100 pi minus 53 pi comes out to negative cosine of 47 pi. See, this is precisely the tactical idea of distributing our numbers between 1 and 100 coprime with 100 over 1 and the same meridian of our planet in such a way that any two numbers that live on the same parallel sum to 100, because this is precisely our first, there will be several such formulas. This is the first divide and conquer, if you will, workhorse formula that delivers this specific transformation. In other words, we just proved that the cosine of 53 times pi over 100, which is one factor in our original product, is equal to the cosine of the green number that lives on the same parallel scaled by -1. And what do we do next? Next, we compute the cosine of the next red number, which is 57. The next red number, 57, or technically 57 times pi over 100, lives on our trigonometric planet on one and the same yellow parallel that it shares with the green number, 43 times pi over 100. In other words, the red number 57, the same yellow parallel runs into the number 43, shown over here again, scaled by pi divided by 100. And that means that according to our first divide and conquer formula, that means that the cosine of 57 times pi over 100 is equal to negative cosine of pi minus the same argument, which is negative cosine of 100 pi minus 57 pi over 100. This comes down to negative cosine of what? 43 times pi over 100. That is precisely the tactical idea behind the design and the distribution of these numbers, and we just proved yet again that the cosine of the red number 57 times pi over 100, which is precisely a factor in our original product of 40 numbers, 40 cosines, is precisely equal to the cosine of the corresponding green number 43 times pi over 100 scaled by the multiplicative constant of -1, and in like fashion we keep applying this transformation to all the red numbers that live in the red hemisphere. 59, which has its friend what? 41, 61, 39, 63, 37, and so on, all the way to the last number over here, which is 99. The logically last red number, 99 times pi over 100, lives on our trigonometric planet on one and the same yellow parallel that the number 1 times pi over 100 lives, which means what? Which means that when we apply the transformation shown over here, red right to left or worked right to left, to the cosine of that red number, we obtain what? Negative cosine of pi minus 99 pi over 100, which is negative cosine of 100 pi minus 99 pi over 100, which is precisely negative cosine of 1 times pi over 100. Again, the cosine of the, loosely speaking, red number is precisely the cosine of the corresponding green number multiplied by -1. Thus, by doing all this lightweight and straightforward work, which is nothing more than the proverbial middle school arithmetic, we have accomplished what? If we enumerate all our green and red numbers consecutively with whole positive consecutive numbers, 1, 2, 3, 4, 5, 6, 7, blah, 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 20, 21, 22, 23, and all the way to 40, then what we just have shown is the following. For all such indexes, which is this upside down A is the so-called universal quantifier for all indexes I that belong to the subset of whole positive numbers starting from 21 to 40 inclusive. This is the closed subset. We just showed that the cosine of the red such number is equal to precisely -1 times the cosine of the green number with the sub-index what? 41 minus I. And that notation should be straightforward to decipher as the indexes I grow, 21, 22, 23, 24, and so on all the way to 40. The sub-indexes of the corresponding green numbers diminish. 41 minus 21 is 20. 22 minus 41 is 19, and so on all the way. The indexes of the red numbers grow, the indexes of the corresponding green numbers diminish, they all meet over here, and that is basically a symbolic representation of our graphical rendition of this whole arrangement. The same yellow parallel connects two numbers that sum to 100. And what does this relation mean to us? It means the following. Since we replaced each and every value of the red cosine with the corresponding value of the green cosine multiplied by -1, and the number of the red cosines in our product is what? Is 20, is a number that is even. Then how many copies of -1 we will accumulate in this replacement? Yes, we will accumulate exactly 20 copies of -1, and -1 raised to an even power comes out to +1. So effectively, when it comes to a product, the replacement of each and every red cosine with the corresponding green cosine will not introduce any pesky -1 in the mix. We can safely throw all this -1 business out. And if we agree that our original product, we will name it as C40 for 40 products of the trigonometric function of cosine, then that original product can be expressed which way? Well, first we will have 20 factors of the green cosines, and then yet another 20 factors of the green cosines evaluated at the very same arguments as we proved in the previous segment. That means that if we designate that new product as G for green cosines, and there will be exactly 20 of those, that will be green product squared, where for the green product of 20 cosines, we will have what? We'll have the product of the values of the trigonometric function of cosine, each of which is evaluated at which argument? G for green sub I times pi over 100. This is nothing fancy, nothing complicated. This is just syntactic sugar, if you will, where the numbers G sub I, the set of numbers G sub I, this is basically our green numbers. 1, 3, 7, 9, all the way to 49. All the way to 49 is basically our original set AI, but it's diminished, but it's cut in half, is twice as small. So these numbers will run 1, 3, 7, 9, and so on, all the way to 47 and 49. These are the numbers taken from here. These are the numbers. So how many factors in this product there will be? In this product, there will be 20 factors, but we have to square that product in order to obtain the value of the original product. Write this down in your paperwork or commit this to memory. We'll come back to it at the end of this episode. And now, what is the number that sits over here between 49 and 51? That number is still 50. 50 happens to have only two distinct prime factors, 2 and 5, still 2 and 5. 2 times 5 times 5. And that means what? That this set over here, shown over here on the bottom left of your screen, is basically the embodiment or the representation of the value returned by what? By the Euler's totient function evaluated at the point n equals 50. Right, exactly. Let me write it down here this way into this way just to make sure. There will be 20 factors or 20 numbers, and these numbers are shown over here. There is no mystery. 1, 3, 7, 9, 11, and so on. 27, 29, 43, 47, 49. And now that you know the technology which unfolds in our first step, try to think on your own what will happen next. In other words, if you were to solve this problem this way, what would your next move be? We suggest that you put this video on pause, walk away from your computer, and think on your own. Before we deep dive into the next step, I want to make sure that we're all on the same page when it comes to the answer to the question, what does it mean to solve each and every smaller and simpler primitive part in this case? In this case, to solve each and every smaller and simpler primitive part means that we take the arguments of the smaller and simpler primitive parts, the trigonometric functions of cosine. We throw these numbers onto the line number segment. We bend that line number segment into a circle. We make that circle one and the same meridian of our trigonometric planet. We put these numbers on that meridian in such a way that any two numbers that live on the same parallel sum to 100, and then we apply to these red numbers the transformation that we showed in the previous segment. Which brings us actually to yet another point. I do not want to muddy the waters too much, but still, to be technically observant, what does that mean? Well, the maneuver that we pulled in the previous segment means that we applied a problem-solving approach that we already studied previously. And what is the name of that problem-solving approach? Correct, the name of this problem-solving approach is reduce and conquer, because we managed to reduce or diminish the size of the original difficult-to-solve problem, the problem of 40 factors, to a problem that is distinctively smaller in size, or a problem of 20 factors. Of course, we have to square the product of 20 factors in the end. Once that is understood, then you should have been able to predict what will be the next step in our solution. And the next step in our solution is pretty much a verbatim copy of what we did in the previous case. We take our numbers that are coprime to 50, numbers 1 through 49. We design a trigonometric planet that is twice as small as the previously designed trigonometric planet, and onto one and the same meridian of the smaller or twice as smaller trigonometric planet, we sprinkle the numbers 1, 3, 7, 9, and so on to 49 uniformly. And because the number of these numbers is still 20, that means that it is possible to divide our trigonometric planet into two logical halves. The green hemisphere that is on your right and the red hemisphere that is on your left. In the green hemisphere, they live the first 10 green numbers coprime with 50, and in the red hemisphere, they live the remaining 10 numbers that are coprime with 50, 27, 29, 31, and so on, 47 and 49. And again, these numbers are placed on the meridian of the smaller trigonometric planet in such a way that any two numbers that share one and the same yellow parallel, such as this one or this one or this one and so on, sum this time to 50. That is right. For example, 37 and 13 is 50. 11 plus 39 is 50. 41 and 9 is 57, and 43 is 50, and so on. 31 and 19 is 50. And what is the next maneuver that we execute? Well, this time we bring our second divide and conquer formula, if you will, shown over here. For all theta real, this relation says that the value of the trigonometric function of cosine is essentially the value of the trigonometric function of sine that is shifted, whose argument is shifted by pi over 2 radians over here, and 2 in the denominator of this shift over here is important. We apply this divide and conquer formula number 2, if you will, to all the red cosines or to all the red arguments. Again, remember that these numbers are shown over here for convenience. Technically, they're all scaled by pi and divided by 100. So if we compute or transform the cosine of 27 times pi over 100, then in this case, what will happen? Remember, just about the only thing that we have to be careful about is this 2, which means that when we bring these numbers, the argument, the numbers that form the argument of the trigonometric function of sine, we have to do what? We have to multiply pi not by 100 as we did in the previous case, but by 50. Exactly. So 50 minus 27 comes out to 23. 27 and 23 live on the same yellow parallel on our trigonometric planet, and that transformation is shown over here. Likewise, we step all the way over the red hemisphere, and we carry out these straightforward computations. There is nothing difficult over here. This is all middle school arithmetic. Again, here we can do all these computations in our mind. We do not really need pen and paper. We just have to be cognizant of the fact that instead of measuring the distance from this number to 100, we measure the distance from this number to what? To 50. The distance between 29 and 50 is what? 21. Consequently, the cosine of this argument becomes the sine, the trigonometric function of sine of this argument 21. 29 and 21 live. 29, jump over here, 21, live on the same parallel of our trigonometric planet, and so on. The cosine of 31 times pi over 100. Again, we can predict what the answer will be. The distance from 31 to 50 is 19, and voila, according to this here formula, the value of the trigonometric function of cosine evaluated at this argument comes out to the value of the trigonometric function of sine evaluated at the argument, which one? 19 times pi over 100. Again, 31 and 19 live on one and the same yellow parallel on our trigonometric planet. Blah, 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 dots, and so on. We walk around the meridian of our trigonometric planet. We pick up all the red numbers. We apply to these numbers this transformation, and we arrive at the fact that the cosine of our logically last red number, 49 times pi over 100, comes out to be the value of the trigonometric function of sine, of which argument? Pi over 100. Again, 49 and 1 share one and the same yellow parallel. And again, when you work on a process of generating a solution for this or that technical problem, it doesn't have to be just a problem in mathematics. It could be the problem in theoretical physics and computer science. It is perfectly fine to try to come up with little helpful stories that sort of depict what is going on in a somewhat playful manner. For example, we can think of these transformations that we carry out as follows. Let's say we jump on the train at the station named 33. This railroad runs over this yellow parallel, and by the time this train takes on the passenger called, the cosine of 33 times pi over 100, by the time this train choo-choos and pulls up into the station that is called 17, and that railroad runs along this yellow parallel, then the passenger that jumps off that train is not really the cosine of 33 times pi over 100, but the sine of 17 pi over 100, and so on. Again, as I remarked earlier, your models or little playful stories may be not that good. They may be awkward and ugly. That is fine. With time, your stories may become better and better, and sometimes when you tell the stories, people actually like them and they are helpful. In any case, to cut the long story short, what does this maneuver that we just pulled by transforming all the cosines of the red arguments into the sines of the green argument buy us? Again, if we enumerate all our numbers with consecutive whole positive numbers, 1, 2, 3, 4, 5, and so on, all the way till 20, then what we just showed is that for all indexes that belong to the closed subset of whole positive numbers that includes numbers 11, 12, 13, 14, and so on, all the way to 20 inclusive, the value of the trigonometric function of cosine evaluated at the red number sub I, this, and this, is equal precisely to the value of the trigonometric function of sine evaluated at the argument green number sub 21 minus I. Again, this is nothing fancy over here. This is just a technical way to show that when the indexes I increase, 11, 12, 13, 14, and so on, all the way to 20, the indexes of our green numbers diminish. So as the red numbers grow this way, the green numbers diminish that way. This is precisely what it means. And coming back to our, remember, green product of 20 cosines, what does it mean? It means that in our green product, we will be able to pair up the value of the trigonometric function of sine, evaluated at an angle blah, with the value of the trigonometric function of cosine, evaluated at the same angle blah. And this is precisely, again, the idea of this logical, visual, tactical device to divide these numbers in half, 10 red numbers, 10 green numbers, or 10 red cosines, 10 green cosines, and then we replaced all the red cosines with the values of the trigonometric function of sine evaluated at the green numbers. These numbers all can be paired up. This number, the cosine of pi over 100, paired up with the cosine of pi over 100. The sine of 3 pi is paired up with the value of the cosine of 3 pi, then sine of 7 pi over 100 paired up with the cosine of 7 pi over 100, and so on, all the way to the very last pair, which is comprised of what? It is the product of the trigonometric function of sine evaluated at the argument 23 pi over 100. This is our logically last green number over here that lives in the green hemisphere, and the cosine, or the value of the trigonometric function of cosine evaluated at the argument 23 pi over 100. Again, all these numbers can be perfectly paired up that way. And what does that mean for us tactically? Tactically, that means, for us, that means the following. According to the double angle formula shown over here, the product of the trigonometric function of sine of an angle theta and the value of the trigonometric function of cosine of the same angle theta is equal to 1/2 of the value of the trigonometric function of sine evaluated at twice the argument theta, 2 theta, twice the argument theta. And what does that mean? That means that in the 20 factors that we had originally in our product, G20, product of green cosines, we'll have precisely 10 pairs of such shape, 10 pairs of such shape. And when we replace these 10 pairs of this shape with their right-hand side image as per this formula, we'll introduce what? We will introduce 10 copies of 1 over 2, as shown over here, 1 over 2 to the 10th power. And these 10 pairs will collapse into 10 values of the trigonometric function of sine evaluated at which arguments? Well, I'll call these numbers, this whole positive numbers, Si times pi over 50, but there is no mystery. These numbers Si are the numbers shown over here, the green numbers that live in the green hemisphere of our smaller trigonometric planet, 1, 3, 7, 9, 11, 13, 17, 19, 21, and 23. And I showed that this product constructed all with these varying numbers Si, 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 and these are just integers that are odd and are coprime with 5. There are 10 numbers in this set, 10 factors in our product, and we have to be careful over here because technically it is tempting to say that these are the numbers that represent the return value of the Euler's totient function evaluated at the point n equals 25, but all the even numbers in this set will also be coprime with 25. We cannot have those. We have to throw these even numbers out. Consequently, we just simply say that the numbers Si are the numbers between 1 and 25 that are odd and are coprime with 5. Do not have 5 in their prime. Factorization, 10 numbers, 10 factors in our product. We reduce it further, and according to reduce and conquer problem solving approach, we went from what we went from 40 factors, then we went to 20 factors, and now from 20 we went to what? 10 factors. 10 factors in our product. This is also a manifestation of the reduce and conquer problem solving approach. And now that you understand the technology that we use in this middle school solution, if you were to solve this problem on your own, what would your next maneuver be? Put this video on pause, walk away from the computer, think on your own. But as a hint, evidently we will take these numbers over here, 10 numbers shown over here. We'll put them on the line number segment. We'll bend this line segment into a circle, design a smaller trigonometric planet, pair these numbers somehow in a way that will allow us to derive a tactical advantage. By now, all our viewers should be on the same page and get on with the program. You try to solve this or that technical problem, and that problem doesn't have to be just a problem in mathematics. It can be a problem in theoretical physics and computer science. Do not be shy and do not be afraid to try to invent helpful stories that will facilitate a deeper and better understanding of the local material that you're dealing with. Trigonometric planets, meridians, parallels, choo-choo trains, boxes, coins, flags, pirates, smoke signals, tennis balls. Anything that works is a fair game. As such, in our case, we take our less, so to speak, 10 numbers between 1 and 25, each of which is odd and coprime with 5. These numbers shown over here, 1, 3, 7, 9, 11, 13, 17, 19, 21, and 23. We design our smallest trigonometric planet yet on one and the same meridian of our smallest trigonometric planet. We sprinkle the numbers shown over here and we pair them up as shown on the upper right side hand side of your screen. We pair up 1 and 23, 3 and 21, 7 and 19, 9 and 17, 11 and 13. And what we do next is what we have been doing all along. We grab the next divide and conquer formula, if you will, that says that essentially the trigonometric function of sine is the trigonometric function of cosine with its argument shifted by pi over 2 radians as shown over here. And we apply this formula to all the numbers that sit on our meridians, and we work, for example, our way carefully. It doesn't really matter. You can do it in real time in any which way, but here I did it from the red numbers 13, 17, 19, 21, and 23, and then from 1, 3, 7, 9, and 11. For example, here, because our favorite irrational and transcendental number of pi enters into this relation over here is pi over 2. When we bring all the numbers that make up the argument of the trigonometric function of cosine under one and the same denominator, we multiply pi not by 50, but by what? 50 over 2, 25. Consequently, when we work with the formula shown over here, we measure all the distances from the numbers that sit on our meridian over here to 25. In other words, the distance from the number 13 to the number 25 is 12. 12 over 50 is 6 over 25. Boom, 6 over 25. The distance from 17 to 25 is 8. 8 over 50 is 4 over 25. 4 over 25. And so on. We walk all the way around this meridian towards the top. And the distance from 23 to 25 is 2. 2 over 50 is 1 over 25. Bam, we have our cosine of 1 times pi over 25. And in exactly the same fashion, we deal with the green number shown on the right hand side of your screen in the green hemisphere, so to speak, and we obtain the distance from the number 1 to the number 25 is 24. 24 over 50 is 12 over 25. 12 over 25. The distance from 3 to 25 is 22. 22 over 50 is 11 over 25. And so on. We come down to the value of the trigonometric function of sine evaluated at the argument 11 times pi over 50. The distance from 11 to 25 is 14. 14 over 50 is 7 over 25. Bam, we have our trigonometric function of cosine evaluated at the argument 7 times pi over 25. No mystery, straightforward middle school arithmetic. And what have we achieved? What we have done right now is we took our product of 10 trigonometric functions of sine, each factor was a sine, and converted this sine into a corresponding cosine. And now our green product of 20 cosines will look as follows. Our divide and conquer problem-solving approach adventures of solving each and every smaller and simpler primitive part took us thus far. We reduced the original product of 40 cosines to a product of 20 cosines, and then we managed to reduce the product of 20 cosines into the following formation. Our product of 20 cosines, which I designated as g sub 20, right now is equal to 1 over 2 to the 10th power times the product of the following 10 cosines, which we obtained in the previous segment. I used the letter C in order to save some space. Basically here C stands for the trigonometric function of cosine. We'll all understand what that means. And the arguments to all these 10 factors, each of which is a trigonometric function of cosine, are the following. 1, 2, 3, 4, 6, we skip 5, 7, 8, 9, 11, and 12 times pi over 25. Now this here product can be evaluated in a number of different ways again, but because I want to reduce this upcoming solution to as simple as possible but not simpler, in order to make sure that the widest possible audience can comprehend that solution, we will evaluate this product of 10 trigonometric functions of cosine using nothing more than the good old middle school trigonometric wizardry. And back in my time, such questions as you see over here were good starter questions for the verbal mathematical examinations to see how the person thinks on his or her feet in real time. And again, remember my comment about inventing helpful stories in order to facilitate a better understanding of the local material that you're dealing with. Such products, such trigonometric products, can be thought of, this is again my idea, my model, you can come up with a better one, as a snake feeding on its own tail. What does that mean? Well, we will see in the next small number of minutes that this product over here basically collapses into another copy of 1 over 2 to the 10th power. And how does that happen and how does that unfold? Well, first we use the double angle identity for the trigonometric function of sine shown over here. This is not a mystery. Remember this formula over here. And first, again, the order in which you work in real time doesn't really matter. You can do it in a different way. You can address the arguments of the trigonometric function of cosine that are in the arithmetic progression 3, 6, and 9. I'll do it next. First, I will do the powers of 2. 1, 2, 4, and 8 as follows. We write down, using the double angle formula, double angle identity, we'll write down an expression for the value of the trigonometric function of sine evaluated at the argument 2 pi over 25 as shown over here. And what do we see here? We see our usual suspect cosine of pi over 25, and this is this guy right here, cosine of 25, pi over 25. Next, we do the same thing for the trigonometric function of sine evaluated at the argument 4 times pi over 25. This will be this number over here. Apparently I forgot 2, I apologize. It will be a 2 over here, like so. And what do we have in this formula over here? We have our second usual suspect, cosine of 2 pi over 25. This is this cosine 2 over 25. And what we do next is we express the value of the cosine of pi over 25 and the cosine of 2 pi over 25 through this relation and this relation. This product is shown over here. This product is shown over here. And that much is straightforward. The cosine of pi over 25 will be what? The sine of 2 pi over 25 over 2 times this sine. And the cosine of 2 pi over 25 will be what? From this relation, the sine of 4 pi over 25 divided by 2 sine of 2 pi. See, these two is important, evidently. But now what do we see? We see that when we construct the product, then what happens? What happens is that the sine of 2 pi over 25 in the numerator and the sine of 2 pi in the denominator cancel each other out. And what do we have? We have left the sine of pi over 25 in the denominator. We write this down. And the sine of 4 pi over 25 in the numerator. But now look at what happens, the magic of this trigonometric product. The sine of 4 pi meets happily the cosine of 4 pi over 25, this guy. You see? So now when this usual suspect sine of 4 pi over 25 meets the cosine here, this formula right here, according to this, is 1 over 2 times sine of 8 pi over 25. So now 8 pi pops out. And this sine of 8 pi over 25 does what? It happily collides with this cosine over here, cosine of 8 pi over 25. And again, according to our formula, the sine of 8 pi over 25 times the cosine of 8 pi over 25, according to this formula, is what? 1/2 of sine of 16 pi over 25. Once we write all these manipulations down, then we will have the following value for the product of the green cosines G20. I will show it in the next segment. Now that we are done taking care of the trigonometric functions of cosine whose arguments are in the geometric progression 1, 2, 4, 8, we do essentially the same to the trigonometric functions of cosine whose arguments are in the geometric progression 3, 6, and 12. I have underlined these factors with red so that you can see them better. The cosine of 3 pi over 25 times 2, 6 pi over 25, and the cosine of 6 times 2 is 12 pi over 25. And we work with these three factors in exactly the same way in which we worked with the similar factors in the previous segment. We take the double angle identity for the trigonometric function of sine, and we use that in order to manufacture all our three cosines: 3 pi over 25, 6 pi over 25, 12 pi over 25. The arithmetic over here is more than straightforward, nothing beyond the proverbial middle school curriculum. 6 is represented as 3 plus 3. 12 is represented as 6 plus 6. 24 is represented as 12 plus 12. All our arguments 3, 6, 12 are present. We now multiply all three relations. We manufacture the product of three factors shown over here, this, and this. And what do we see? We see again the miracle of cancellations. In other words, the value of the trigonometric function of sine on the left-hand side of the equal sign, 6 pi over 25, will cancel with the value of the same function on the right-hand side of the equal sign. And the same thing will unfold for the trigonometric function of sine, evaluated at the argument 12 pi over 25 on the left-hand side of this equal sign and on the right-hand side of this equal sign over here. And as the result of these cancellations, what will survive? Well, we will pick up 3 extra copies of 2, 1, 2, 3. And these 3 copies of 2 will jump to the other side of the equal sign in the denominator shown over here, 1 over 2 to the 3rd power. In the numerator will only survive what? The sine of 24 pi over 25. And what will survive on this side? On this side, the only factor that will survive will be the trigonometric function of sine evaluated at the argument 3 pi over 25. It will jump in the denominator of the result. And once we slug in this result over here, then we will obtain the following result. I will show this result in a few seconds in the next segment. I just want to make sure that we all understand where the 4 extra copies of 2 came from the previous segment. 1 copy of 2 came from the cosine of pi over 25. Another copy of 2 came from the cosine of 2 pi. And remember, we had the avalanche of sine of 4 pi showed up, and then the sine of 8 pi showed up. So that's altogether 4 extra copies. 10 plus 4 is 14. This is why we have 14 over here. But in the next segment, the number that will be over here will be what? 3 plus 14 precisely. That number will be 2 to the 17th power. In order to make sure that we're all on the same page, compare your records to mine. The value of the green product of 20 cosines right now looks as follows. 1 over 2 to the 17th power plus 2 sines, 2 trigonometric functions of sine of this argument pi over 25 and 3 pi over 25 in the denominator. And in the numerator we'll have the following 5 factors. Sine, the trigonometric function of sine. I use the abbreviation over here S for sine to save some space, of 16 pi over 25 times the sine of 24 pi over 25, and the cosines. This is the usual suspects from the previous segment, 7, 9, and 11. Now we work with these guys, the sines of 16 and sines of 24 pi, these 2 factors. We use this formula over here. Let me perhaps frame it so you guys can see better. This formula over here, we used it before, but now according to this formula, the sine of 16 pi over 25 is what? The distance between 16 and 25 is 9. Boom, we have 9 pi over 25 for the same trigonometric function of sine. And the sine of 24 pi over 25 is, again, according to this formula over here. The distance from 24 to 25 is 1 pi over 25. What happens next? Sine of 1 times pi over 25 here and here cancel out, you see. Now this is gone. And once we enter the sine of 9 pi over 25 into that product, essentially we're erasing these guys over here from the formula. The sine of 9 pi over 25 will happily collide with what? With this cosine of 25. So when these guys enter into a productive relationship, what will happen? Well, we use again the double angle identity for the trigonometric function of sine. The sine of 9 pi over 25 times the cosine of 9 pi over 25 is 1/2 of what? Of sine of 18 pi over 25. But again, according to the same very formula, this formula over here, this can be rewritten which way? This becomes 1/2 of the trigonometric function of sine of what? 7, let me even highlight it for you, 7 pi over 25. 7 pi over 25. And what do we see again? I will erase the board right now to keep things neat. But you already understand where this is going. We have the sine of 7 pi. And what is here? The cosine of 7 pi. These 2 guys collide and produce an interesting and result that is very useful to us. After all the intermediate steps, our green product of 20 trigonometric functions of cosine looks as follows. 1 over 2 to the 18th power. Recall from the last segment we picked up 1 extra copy of 2. The sine of pi over 25 is gone. In the denominator we only have the trigonometric function of sine evaluated at the argument 3 pi over 25. And in the numerator we have the following 3 factors. The cosine of 7 pi over 25, the sine of 7 pi over 25, and the cosine of 11 pi over 25. we understand where this factor come from. Again, we roll up this product into what? According to the double angle identity for the trigonometric function of sine, we roll up the product of these two trigonometric functions of cosine and sine of the same argument into 1/2 of the sine of 14 pi over 25. But magically enough, again, by this formula, the distance between 25 and 14 is what? 11. So essentially what we have here is 1/2 of the value of the trigonometric function of sine evaluated at the argument 11 pi over 25. And looky look, another miracle, we have the cosine of 11 pi over 25 sitting precisely left over. So now essentially this factor is gone, this factor is gone, and these two factors are replaced by what? 1/2 of sine of 11 pi over 25. Extra copy of 2 goes over here. So now we have 2 to the power of 19. And again, we roll up that product into cosine of 11 pi over 25 times the sine of 11 pi over 25 becomes 1/2 of what? 11 plus 11, 22. But by this formula, the distance between 25 and 22 is 3. So essentially what we have is 1/2 of the value of the trigonometric function of sine evaluated at the argument 3 pi over 25. And look again, another magical coincidence. We have the sine of 3 pi over 25 in the numerator and the sine of 3 pi over 25 in the denominator. What happens next? These trigonometric functions cancel each other out. 2 copies of 2 picked up over here. 2 to the power 18 plus 18 plus 2 is 20. So now we have the following result. The value of the product of 20 trigonometric functions of cosine g20, to which we referred before as g20, is 1 over 2 to the 20th power. But remember, in the earlier segments, we proved that the square of that product is the value of the original product shown over here, where the numbers ai are all the numbers that are what? Between 1 and 100 that are coprime with 100. G squared, 1 over 2 to the 20th power squared becomes 1 over 2 to the power of 40. And this is the answer that you were expected to produce. Again, before we move on to the next challenge, and essentially we're done with the mathematical problem S2E41, I would like to make the following remark, that whenever we conduct a mathematical experiment, and what just transpired over here is exactly that, a mathematical experiment, the result of each and every mathematical experiment sits on the receiving end of a certain, in some sense, bigger, wider, and deeper mathematical machinery or layer of mathematics. We may know about this machinery and about this layer, or we may not know about this machinery and layer. But regardless of our knowledge or not knowledge of that layer and machinery, the result of each and every mathematical experiment does sit on the receiving end of that of certain wider, bigger, and deeper machinery. Again, in this case, of course, and quite often in grown-up mathematics, such products will be evaluated using complex numbers, and once you go that road, inevitably pretty much you will run into the so-called cyclotomic polynomials. But in order to make sure that the widest possible audience can comprehend the solution of this problem, I reduced it to middle school arithmetic, nothing more than trigonometric wizardry of middle school, and this is the result. We're done with the problem S2E41, and we will move on to a new challenge next. Our next challenge will be also a mathematical problem. S2E41 is shown over here. And in that challenge, using precisely the divide and conquer problem solving approach, we're asked to evaluate the following limit. And the structure of that limit is the following. 1 over n cubed times the finite sum that runs over the dummy summation variable k, where the values of k change from 1, 2, 3, 4, 5, and so on till n, where n is a whole positive number. And the summation, the summand in this case looks as follows: k times the square root of n squared minus k squared. One more time, the limit of 1 over n cubed times the sum of the following summand, k times square root of n squared minus k squared, and the summation, the dummy summation variable is k, and it varies from 1 till n, where n is a whole positive number, arbitrary number, and the limit is evaluated when n tends to positive infinity. Again, the intended solution over here has to use the divide and conquer problem solving approach. That problem is actually quite difficult. I will put an asterisk on it. I'm not really sure how many people will be able to solve it, but try to go over the material that we covered that described how the divide and conquer problem solving approach works, and see if you can come up with an interesting story behind the answer of why the value of this limit is what it is. This is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will share my solution of the mathematical problem S2E41.